Hey everyone.
Good afternoon, Ghana.
Good afternoon.
Good afternoon.
Joe, enjoyed the test?
Yeah, it was a lot easier this time.
Well, let's get started. Is there anybody who would like, are there any problems that anyone here would like to work on in particular?
I was thinking number 11.
Okay, I'll take that one.
I'll just really quickly say I also sent out all the test scores and results, I guess last night for me. So you guys all should have gotten them today. So check your email if you haven't seen them.
Okay, let's take a look at problem number 11. Describe a divisibility rule for 24. How do we know that an integer is a multiple of 24 most easily? Anyone here have any ideas?
We put it in mod 24 and see whether we get a residue of 0.
Okay, that'll definitely work, but is that going to be any different than just doing long division and finding the remainder?
It has to be divisible by like 3 and 8. So then we'll know 24, is divisible by 24 too.
Okay, yeah, 24 is equal to 2 to the third power times 3 to the first. And if we wanted to, we could say, well, you know what, something is a multiple of 24 if and only if it is a multiple of 8 and a multiple of 3. And part of this depends on the fact that the GCD of 8 and 3 is 1, and the LCM of 8 and 3 is 24. So yeah, we can break this down into two pieces and say we're looking for something that must be a multiple of 3. And a multiple of 8 simultaneously. And here's a potential example. And what's the divisibility rule for 3?
The sum of the digits should be divisible by 3.
Okay. And what is the divisibility rule for a multiple of 8?
The last 3 digits in the number should be divisible by 8.
Good. Yeah, we form an integer from the last 3 digits and we test to see whether or not that's a multiple of 8. Why does that work?
I think because 8 is a divisor of, 1,000. So it just continues.
Good. Yeah, this is 43 times 10 to the third plus 536. And 43 times 10 to the third is already a multiple of 8 because 10 to the third has 3 powers of 2 in it. So we don't have to worry about everything to the left of those last 3 digits. It's already a multiple of 8. So any remainder that we have, 0 or otherwise, will come from just that integer formed by the last 3 digits. Any questions or thoughts about this one? By the way, once we finish the problems, I'm going to do a very brief lesson. We didn't quite get to the divisibility rule for 11 and using modular arithmetic to see why that works, but we're also going to come up with a divisibility rule for 999,999, and possibly other things at the same time. All right, what's another
I guess
problem?
I have a quick question.
Yeah.
Based on what I saw, do you want to quickly explain why it works if you apply the divisibility rule for 3 and 8, but not if you do, say, 4 and 6, which I saw some people wrote down?
Okay, so let's say that you, let me come up with an example that's non-trivial. Let's see. Okay, this number right here, if we add up the digits sum to 12. And it, let's see, divisibility rule for 6. Well, a divisibility rule for 6 would be that it's a multiple of 2 and a multiple of 3, perhaps. Or you could just divide by 6, either one. So this number right here, it turns out that it is a multiple of 4. The last 2 digits form a multiple of 4, and we talked about that divisibility rule. It is also a multiple of 6. But here's the thing, it is not a multiple of 24. That's not good enough to tell us it's a multiple of 24. If we take these two facts right here, we know that an integer is a multiple of 4. We know that it's a multiple of 6. Therefore, it is a multiple of the LCM of 4 and 6, which is 12. Not 24. We can only say that this integer is a multiple of 24 when we say it's a multiple of 4 and a multiple of 6. This is why it's good to break down the prime factorization and pick divisibility rules that collectively have a least common multiple of 24, or possibly some multiple of 24. Well, I think if you're talking about a divisibility rule, you want it to be exactly 24. And that's why we want all 3 powers of 2 grouped together. If they're never all grouped together, then you never know for sure that you've tested for all 3 of those multiples of 2 at once. Does that make sense?
Yeah.
Good. Thanks, Wendy. All right. What's another problem anyone would like to take a look at?
Question 12.
Okay. Question number 12. This is a real tough one right here. I'll let Wendy take this one.
All right. Let me figure out my screen share real quick.
Actually, Wendy, if you want, I can take this one. I wrote up the solution to it.
Oh, yeah, sure.
For there. So I've got this fresh on my mind.
Go for it.
It's a great problem to end a test like this with, because there are a number of elements in here. Well, let's see. We've got a convex pentagon with vertices A, B, C, D, and E. And we're coloring, let's see. Okay, we're coloring the vertices, one of any of 6 different colors. And maybe we can just label those colors 1, 2, 3, 4. Actually, I don't want to do this with numbers because we're going to compute with numbers. We'll come up with something in a moment. But we're told that whatever the colors are, that they must be different along the diagonals. So, if A is blue, D cannot be blue. If D is green, B cannot be green. So this might be such a coloring, and it only uses 3 colors, but that's allowed. We can use 3 of the 6 colors. In fact, we can only use up to 5 of them. So what makes this, I think the first thing that makes this easier is to realize that there's only one sort of path that you can walk along the diagonals. That if we were to redraw this, we could redraw it out closer to a circular formation. And if we put A up here, well, what is A connected to along the diagonals? A is connected to C, and A is connected to D. And then C is also connected to E, and E and D are connected to B along the diagonals. So we could consider ourselves sort of unknotting the pentagon. And this isn't strictly necessary. I just think that it makes things feel a little bit easier. If we were to unknot the pentagon in this way, this is what the coloring would look like. And now we're just saying, hey, we want no two adjacent vertices to be the same color. And I think that gives us a little bit easier of a setup to think about. So, okay, no two can be the adjacent vertices can be the same color. Well, without loss of generality, we can say, hey, there are 6 colorings for A. No matter, like, any kind of coloring that we come up with, and maybe we label the colors M, N, O, P, Q, and R. And let's say we pick some coloring, maybe, and I'll start at A, and I'll go clockwise. Maybe we pick the coloring N, P, N, R, M. Well, if I wanted to, I could rotate this coloring in terms of the letters. I could replace N with the letter after N, P with the letter after P, N with the letter after N, R with the letter after R, and just kind of go around to M, and then M with N. And so we can always take any one coloring and sort of go to the next color for each color there and get another coloring. What this means is that for each color that we have, for each coloring right here, there will be one coloring that begins with each of the other colors that are sort of grouped together in this way. And so there will be just as many colorings that start with each color. There's a symmetry in that regard. I feel like I didn't explain that the best I could. Is that clear that, that there are just as many colorings where A is blue as there are where A is green?
Yes. Let's do the fact that since the colors can be associated with 5 other different colors, you could have A be blue and it's still associated with the other colors, and you can associate green with the same amounts of colors as you associated with blue.
Good. And this technique, this use of symmetry, we often use the phrase without loss of generality. Wendy, have you used this phrase in class during your first couple of weeks?
I haven't yet.
Okay. So this phrase right here, it indicates that we're taking this symmetry into account. And so whatever answer we come up with, we're just going to multiply it by 6, but we're going to start and say, that first vertex is some particular color, and maybe that color is blue. And now we've got these other 4 vertices to worry about, but we can do something similar. The one to the clockwise position from blue, we could say, well, it can't be blue, so it must be some other color. Maybe we'll make that green. And we can do that in 5 ways. Now, every single coloring will have, these 2 choices for colors. Well, there will be 6 times 5 different ways we can make those 2 choices. So now we're really down to just looking at 3 slots. That makes life easier. So I'm going to kind of leave these last 2 slots until the end. because it's going to depend a little bit on what we put, or, once we pick, whatever it is that this slot, whatever color we put there, those last two slots will be kind of easier to choose, right? But there are two different ways that we could color that slot with the star under it. Well, one of those ways, and this will be case one, I'm going to call this the star slot. And let's say that the star slot equals green. So if we go blue at the top and green flanking it, what's true about the last two slots at the bottom? What colors could they be?
Red or green?
Well, they can't be green. If we put green right here, then neither of those two slots at the bottom can be colored green. Those vertices.
Blue and red.
So they could be red. Tell me everything that you know about them, knowing that the two middle slots along the flanks are green.
Then both slots will be red.
Why do they have to be red?
Because that's the only color left since the A is blue and then
Hello, mommy.
B and C is green.
Well, let's be clear. We have 6 total colors. So red is not the only color left. Let's say those are the colors we're choosing from. 6 total colors to choose from. No two adjacent vertices after we've untied this knot and arranged them in a circle. No two adjacent vertices can be the same color. So how could we color the two at the bottom?
We could pair them and make them have the same color, either red, purple, orange, or black.
Make them have the same color?
Yeah.
But we can't have any
They could
two
have-
adjacent that are the same color.
They should have different colors.
They should
So
have different colors.
Red, purple, orange, and black.
Red, purple, orange, or black. Why not blue?
Okay, yeah, or blue.
Okay, so they have to be different colors, but they can't be green. Green is the only color that we could not possibly color either of them green, right? But they do have to be different colors. And how many ways can we choose those two colors?
I think 20.
5 times 4.
5 times 4, which is 20. Good. Well, that's case one. And of course, it's not just going to be 20. It's 20 times that 6 times 5 at the top, but we'll multiply that in later. So now case two. So if that star isn't green and it can't be blue, right? We've used up that possibility. Then we could let the star be any of the other colors. It could be red, purple, orange, or black. I'll use K for black instead of B, since B might be blue. So red, purple, orange, or black. So that's 4 options right there. And you know, does it matter which one we pick to see what happens?
No.
It doesn't.
Yes, of course.
You know, I mean, it will change what the others can be, but it won't change the total, right? For instance, if I color this one right here purple, then it's still the case that the two at the bottom can be anything but purple and green, anything but those two colors. Well, and you know, the bottom left one could be green and the bottom right one could be purple, right? But basically we have two colors that restrict those two slots. And that's true whether we chose the one on the left to be purple or orange or black or red. So we might as well just examine one of those cases and then see what happens from there. And then we'll multiply our total by 4, one for each of those 4 possible colors. Okay, so let's say that we've chosen purple. Now, in how many ways can we fill those 2 bottom slots? Now, I'm going to divide this into 2 cases once again. So we're going to have subcases. In case 2A, I'm going to pick, and I'll call this the double star slot. I'm going to pick green. That way, this last remaining slot that we're choosing the color for, it can be anything except that one color, green. And how many ways can we do that?
5.
5 ways. Good. So for case A, we have, case 2A, we have 5 total possibilities. And then for case B, I'm going to let star slot be any of the other remaining colors. Well, it can't be purple, but it could be blue. It could be red. It could be orange, or it could be black. And then in how many ways can we choose?
Shouldn't black be K?
Say again?
Shouldn't black be represented K instead of?
Oh, you're right. You're right. Apologies. Thank you. So if we pick blue, for instance, and how many ways can we pick the color for the last vertex?
2.
What did you say, non-orally? I couldn't quite hear you.
2 ways.
Well, what could we not pick for the last vertex?
2.
Blue and green.
Blue and green, right. Those are the only colors we can't pick. So there are 4 possibilities. Okay, well that's 4 possibilities for each of these 4 colors that we could pick. It's going to be the same for each of them. So we've got 4 times 4 ways to pick the options in case 2B, but we've got a multiplier of 4 on case B because we're on cases A and B because we could have started with any one of those 4 colors to fill in slot star. And now it's just a matter of doing computations. Now we have a multiplier of 6 times 5 for everything. That was our original choosing of the very first 2 colors. Then we have case 1, in which we had 5 times 4 ways to pick the colors of the last 2 vertices. And then we add to that case 2, where we had a multiplier of 4 ways to pick slot star. And then within case 2, we had case 2A, where we had 5 possibilities, and case B, where we had 4 times 4 possibilities. And now we compute. 30 on the outside, and then 20 plus 4 times 21. And what do we get in total here?
1,350.
More than that, inside the parentheses, what do we get?
Is it 104?
104.
104. And 104 times 30 is
3,120.
3,120 different ways to color the vertices. So good challenging problem right here. We've got, first of all, we've got this model that we drew, right? We've got, and we call this a graph. And I don't know if any of you have heard that term before, when we use dots and lines to represent a figure. And this problem was written by somebody who had probably done different kinds of colorings of vertices of graphs before. But they made it a little bit more challenging to think about by saying, hey, it's not just the adjacent vertices of the pentagon that can't be the same color. Oh, it's those vertices along the same diagonal. But we figured out that we could unwind that and just make it into a pentagon type figure where adjacent vertices can't be the same color. So that was a little bit easier to think about. And once we did that, we used casework and sub-casework. And our casework was, we had, without loss of generality, we had a symmetry. We had 30 different ways we could choose the first two colors that we chose. And I just made those the top and the top right vertex. And then we were doing casework based on the last three vertices that we chose. And it was really the first of those three vertices that was the basis for how we broke down our two big cases. And second to last vertex was the basis for how we chose our subcases within case two. And there's so much of counting and combinatorics that comes down to good organization. And good organization is a skill that you build up, just like you learn to handle more lines of algebra when you do algebra. Any questions about this one?
Yeah. The P there representing purple for the vertex on the left. Does it mean that there are 6 possible colors for it?
No, at the point at which we'd chosen blue up at the top, and for case 1, we chose green in that slot. So purple was not one of 6 possible colors we could have used to base case 2 on. It was one of 4 possible colors. And that's where that 4 multiplier comes from right there. It couldn't be blue, and we had already covered the case where it was green. Is that clear?
Yes, thank you.
Mr. Crawford, I was also wondering if you could work it out by sort of counting the remainder of colors left. Like we chose one color and we're working in the case of you have 2 of the same color. So you pick one color, then you have 5 left, and let's say you move to a spot which allows you to have that same color. You still say you have 5 left, 5 colors left to choose from, and you sort of just multiply and then add.
Yeah, absolutely we could. We could say, we could do the case where it's 5 different colors. That might be our case 1, and the number of ways we could choose those would be 6 times 5 times 4 times 3 times 2. So really, say 6 factorial divided by 1 factorial, but that's just 6 factorial. And then case 2 might be 3 colors once, and 1 repeated color. And there are 6 ways to choose the repeated color. That would be the first thing that I would want to do. And then there would be 5 choose 2 ways to choose the locations of that one color. And then for the last 3 uncolored vertices, there would be 5 times 4 times 3 ways to color those. And I want to do this carefully because I haven't worked it this way before, so I want to make sure that I'm not botching anything here. Let's see. 6 ways to choose the repeated color. 5 choose 2, that's 10. And then 5 times 4 times 3 ways to color the remaining nodes. This seems like it's too big. And what am I missing?
You might have overcounted some of them.
Why would I have overcounted some of them?
Because first you have you're choosing a color to be repeated. So wouldn't it rather be 5 choose 1 for choosing a color to be repeated out of the colors that are available?
Well, we have 6 total colors. Okay, so here's what I've done. There are 6 ways to choose the color that's repeated. And 5 choose 2 ways to pick the nodes that it could be on. And then there are 5 choose 3 ways to choose the remaining 3 colors, and 3 factorial ways to color them.
Oh, yeah, I see it now. So basically, what you did is that you multiplied the colors, how many colors there are you can choose from, and then you multiplied the how to select the 2 pairs that you will keep the same, and then the 3 that won't be the same times the number of ways in which you can choose those colors.
But this is still far larger than our answer. Oops. I don't know why I've got a 60 there. Should just be a 6. But this right here would be 3,600 different colorings alone, and that's bigger than our answer of 3,120. So what's wrong with this?
You've overcounted some of them.
How have I overcounted some of them?
You might
Because you
have rotated. If you rotated the pentagon, you would still be basically working with the same color. So that might have caused you to overcount those rotations.
Well, we can rotate and get a different coloring. This isn't like arrangements of people sitting around a table. We don't have that circular symmetry because we consider the vertices distinct for the purpose of this problem. They're labeled vertices.
Okay.
But this is a good puzzle right here. Why does this overcount? Well, let's come back to this. Are there any other cases?
Is there a case where you're repeating two colors and you just have one regular?
Okay. So, by the way, I'll go ahead and point out, actually, let's finish case 2 before we go on. I'm going to highlight the mistake. Why is that a mistake?
5 choose 2 is the same as 5 choose 3.
It's not that. What's true about the way that we color the vertices?
It can be along the diagonals.
You can't have the same color in particular positions. If we untie the knot, we could just say you can't have two neighbors that are the same color. And here we've counted those into the possibility. I just said 5 choose 2, choose any 2 of the vertices to label that color. But we didn't correct for the fact that we can't have 2 neighbors that are the same color. So instead of 5 choose 2, how many ways are there to pick 2 vertices to be the same color?
Isn't there 4 ways along the diagonals, just like D and E can be the same, A and B can be the same, A and E can be the same?
There's more than 4.
Is it 10?
Whoever said 5 had it correct. And you could do it with complementary counting. You could say there are 5 ways to choose 2 that are adjacent. And we want any of them but those. So what we really have here is 5 choose 2 minus the 5 where they are adjacent. And that gives us 1800 for case 2. I think, if I've done my arithmetic correctly. And then finally, with case 3, we could have 2 of 2 different colors and 1 of another. And we could pick the 2 colors to be repeated in 6 choose 2 different ways. And we could pick the 1 color in 4 choose 1 different ways. But now we need to come up with the arrangements. If we pick the colors, well, we could go, let's see. I would maybe pick the color that's not repeated first. Maybe put it up at the top. And then multiply the answer by 5 when we're done. So maybe color the top vertex red. And let's say that blue and green are our 2 other colors. And how many ways can we pick the remaining colorings?
Three.
4.
Well, if we color this one blue, what's the next one in counterclockwise order?
Green.
It has to be green. And what's the next one?
Blue.
Has to be blue. And what's the next one?
Green.
Green, right. So once we pick just that vertex, The rest is determined for us. So there's only just 2 ways to do that. So in total, this case will be, we'll have 6 choose 2 ways times 4 choose 1 ways to choose the colors, and then 5 ways to choose which vertex is the lone colored vertex, and 2 ways to pick the remaining ways to color everything. And we get, for this case, 600 possibilities. And if we add the 3 cases that we've come up with together, we get 3,120 once again.
I think I understand this method better than the star one. Yeah.
Okay. And there are very often more than one way to work a combinatorics problem, and if one of them feels more comfortable, then great. One advice that I try to encourage people to take, early on learning, practicing casework organization and combinations is as best you can, focus on the one that doesn't fit your thinking as well. Learn both, and if you can apply both, they'll help you in different ways on different problems. So try to force yourself to think through the one that you don't feel as comfortable with.
Okay.
And we will post this video of office hours, so you can all look back at this. And this is actually a tough problem to discuss and to put into words without having prepared it. So it may mean that I have given better and worse explanations for pieces of this. So it may be good to watch this again anyway. All right. What's another problem that anyone here would like to take a look at?
Number 10, the card one.
Okay, I will let Wendy take that one.
I realized that was muted. Okay. Cool. So this problem, right?
Yes, please.
All right. So this says the game uses a deck of n cards. We know n is an integer greater than or equal to 6. And then it says the number of possible sets of 6 cards that can be drawn from the deck is 6 times the number of possible sets of 3 cards that can be drawn. And then they want you to find what n is. So we can decompose this one a bit. Oops. Sorry. All right. So basically there's 2 parts and we want to maybe write an equation with this. So it's basically saying if we can write down the number of sets of 6 cards, that equals 6 times number of sets of 3 cards. So here I'm just translating the word problem into an equation so we can start solving for n. And then now that we've broken this down, we see there's actually kind of 2 sub-problems here when it comes to counting. So if we have n different cards, how many ways are there to pick 6 cards from it? Does anyone know that or remember that from class? It's a little tricky because there's n now.
Are there n choose 6 ways?
Yeah, so n choose 6. which we can write like this for now. And then what about number of sets of 3 cards?
And choose 3.
And then if we remember how to actually calculate n choose 6 or n choose 3, we can do a quick example. So for example, like 7 choose 3 is just 7 factorial over 7 minus 3 factorial minus 3 factorial. So here we can write this out as well. So here this is going to be n factorial over n minus 6 factorial times 6 factorial equals 6 times n factorial over n minus 3 factorial times 3 factorial. And for me, what I like to do is actually expand this out because it's hard to really think about a bunch of factorials. And so here on the left, what we get is n factorial, remember, is n times n minus 1 times n minus 2 times n minus 3. I'll write down not the whole thing, but enough to does everyone see why that's true? And then on the bottom, we have n minus 6 factorial times 6 factorial. Over here, we can write this as n factorial is n minus 1 times n minus 2 times n minus 3 factorial over n minus 3 factorial times 3 factorial. Any questions on this step? So here I expanded out n factorial a little bit, and we know that there's at least this many elements because the problem said that n is greater than or equal to 6. All right, so now we can do some cancellation. So here you have this. We can also cancel on both sides of the equation. So I'll use a different color. So here on the left, we have n minus 1, n minus 2. We can just sort of divide both sides of the equation by that. We can also say multiply both sides by 3 factorial, and that gives us 6 times 5 times 4 on the bottom. So now we have this equation after we've canceled out some factors and then also multiplied both sides. We get n minus 3 times n minus 4 times n minus 5 over 6 times 5 times 4 equals 6. So I did a lot of stuff in that step. Does anyone have any questions? I can also write down the sub-step.
I was wondering what you factored out to remove n times n minus 1 times n minus 2, and then the numerator for the n over 3 factorial.
Yeah, okay, let me go back a little and maybe write it out a little bit differently. Okay, so do you see why the left side can be written as this and the right side can be written as that?
Yeah.
Okay, so let's just simplify this fraction on the left. So we can basically cancel out common factors in the numerator and denominator, and also on this side. So this is kind of saying 7 choose 3 is equivalent to 7 times 6 times 5 times 4 factorial over 4 factorial times 3 factorial. And then I'm just canceling out the 4 factorial.
Okay.
Okay, so then after I did that, if I write down what I have here, I have n times n minus 1 times n minus 2 times n minus 3, n minus 4, n minus 5 over 6 factorial, and that equals 6 times n times n minus 1 times n minus 2 over 3 factorial. So now to kind of simplify this, so we can always multiply both sides of the equation by something and the equation will still be true. Similarly, we can divide both sides of the equation by something as long as it's not 0, and that the equation will still be true. So we can try something like, let's multiply both sides by 3 factorial. And then if we do that, then we see this 3 factorial cancels with this 3 factorial. And then this 3 factorial cancels with part of the 6 factorial, because 6 factorial equals 6 times 5 times 4 times 3 factorial. So this 3 factorial can cancel with this 3 factorial. And if we do that step, then we will get n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 over 6 times 5 times 4 equals 6 times n minus 1 times n minus 2. All right, and then we'll do another of the same thing, but instead of multiplying both sides by 3 factorial, we're gonna multiply both sides by a common thing, which is n times n minus 1 times n minus 2. And the reason we want to do this is we actually see that there's sort of this common factor here. So we actually want to cancel it out. So if we multiply both sides by 1 over this value, or divide by n times n minus 1 times n minus 2, then what we can actually do is cancel these two and cancel these two. And so if we do that, then the equation further simplifies. Then we end up with n minus 3 times n minus 4 times n minus 5 equals, over 6 times 5 times 4 equals 6. Any questions about getting to this step? All right, so we're gonna move stuff around in the equation again. So now what I kind of want to do is move all the things, all the factors with n on one side and then all the numbers on the other side, because it's kind of hard to work with a fraction here. And so I want to move basically this quantity over to the side. And the way I'm going to do that is I'm going to multiply both sides by 6 times 5 times 4. And on the left side, we can cancel. So this gives us n minus 3 times n minus 4 times n minus 5 equals 6 times 6 times 5 times 4. Any questions until here? Okay, so at this point, there's like various ways you could do to solve this, but what I did here, instead of multiplying this out on the right, which I feel like doesn't help you too much, you can kind of interpret this equation as you're looking for 3 consecutive numbers, and their product is equal to 6 times 6 times 5 times 4. And so one of the reasons I picked this problem is because you all were learning about number theory and divisibility. And so basically, if you have a number that can be expressed like this. Basically, we want to see if we can rearrange the factors such that we write it as the product of 3 consecutive numbers. And here, what I did is just kind of trial and error a little bit to solve this. And so there's like, I guess, different ways you can trial and error, but for me, I kind of eyeballed it. 3 consecutive numbers means that you have 3 numbers that are kind of around the same size. So you don't have something like 2 and 10. It's like the numbers are very close together. And then on the right, you have a product that's 6 times 6 times 5 times 4. And so this is roughly, I guess you could calculate this out. This is roughly 7, 20, if I did that right. And so if you kind of look at roughly what the cube root of 720 is, or sort of what we would get if we tried to find approximately 3 numbers that multiply to that, you might get something like, oh, well, it's around like 8 or 9, because 9 cubed is 729, right? So you might think, okay, the 3 consecutive numbers are probably around like 9, 10, 8, something like that. So you can kind of try it out. And so actually, that actually happens to be the right answer here. So 720 is kind of close to 9 cubed. And then if you kind of look around 9 cubed, you'll see that 8 times 9 times 10 is actually 720. So that's kind of one way you can do that. You can also look at kind of the factors here and say, okay, I have 6 times 6 times 5 times 4. That's equal to 2 to the 4 times 3 squared times 5. And so if I wanted to find 3 consecutive numbers, I'd have to have one that's sort of a factor of 5. Maybe 10 would be a good candidate. I have 9, and then I have 2 cubed left. So that gives you 10, 9, and 8. It's kind of various ways you can do that. And so if we find 3 consecutive numbers whose product is 720, then these numbers map to n minus 3, n minus 4, and n minus 5. So here we could say that n minus 3 is 10, n minus 4 is 9, n minus 5 is 8. And their product, if I were to multiply these all together, is n minus 3, n minus 4, n minus 5, and that equals 720. And so if this is the case, then we can easily see that n equals 13. Any questions? Are there any other questions people want to see?
Question 7. Did we do that?
Sorry, I don't think I heard. Which question?
Question 7.
7. Okay. Can you remind me quickly which one that was?
I think that's your number 4, Wendy.
Okay, thanks. Is it this one?
Oh, it is the
Oh, no, actually.
the
24 permutation.
That's one of mine. I can take that one.
Okay, cool.
Okay. There are 24 different permutations of these 4 even digits, and we want to count how many of them are multiples of 4. So just to write down some examples: 2, 4, 6, 8, 2, 6, 4, 8, 8, 6, 4, 2. But in order to determine whether or not something, one of these 4-digit integers, is a multiple of 4, we just need to look at the last 2 digits. But I want to point something out. If our second to last digit is, for instance, 2, then there are 3 possible ways we could choose the last digit. Make it 4, 6, or 8. And now we just need to look at which one of these numbers, in order to determine whether or not something is a multiple of 4, we only need to look at the last 2 digits. That's our divisibility rule. And we notice that this one and this one are multiples of 4. So now we could just go through each way to fill out a tens digit. And notice for each of these also, like whatever the first 2 digits are, there are 2 factorial ways to choose the first 2 digits. And so, we don't just have 2 possibilities here, we have 4 possibilities, but we need to go through each of the tens digits and see how many ways we can pair it with a units digit that give us a multiple of 4, and then multiply that by the number of ways to arrange the first 2 digits. And if we go through all these, we get, I think, 2, 1, 2, and 1. Two where 6 is the tens digit, and then with 8, let's see, 8, 2, 8, 4, 8, 6. Just one of these. So 6 out of the 12 possibilities times 2 factorial gives us 12 different ways to construct one of those multiples of 4 out of a permutation of those 4 digits. I couldn't understand. Can you repeat? Whoever was asking a question, you cut out on us. Okay, well, we'll move on to another problem. Any other problems anyone would like to take a look at?
My apologies,
Question
but it seems I had a network problem. So could you please go over that question?
Okay. All we need to determine whether or not an integer is a multiple of 4 is to look at the last 2 digits. So we could take a look at all the 12 different ways to pick the last 2 digits and figure out which ones of those are multiples of 4, and then multiply by 2 factorial, because that's the number of ways that we could choose the first 2 digits. So I found 6 ways to make a multiple of 4 out of the last 2 digits, giving us 12 total. And just for example, like when we find that 2, 4 is a multiple of 4, we can say 6, 8, 2, 4 is a multiple of 4, and 8, 6, 2, 4 is a multiple of 4. And I'll tell you, one thing that I do also is I look at 2 and 6 as being kind of the same, and 4 and 8 as being kind of the same. If you add 4, subtract 4 from between those digit pairs, you're not changing whether or not something is a multiple of 4. So it's kind of like parity in a sense. And once you realize that, you realize that that you're trying to actually no, that's not true. No. Here's the easier way to think of it. Since we're only using even digits, and any multiple of 20 is already a multiple of 4, then we realize that the tens digit we choose doesn't even matter, right? If we're building off of, let's say, 8620 or 8640, and we're just picking, the last digit needs to be a multiple of 4. So the only ones that work are the ones where the units digit is a multiple of 4. So there are 2 ways to pick the units digit, and then 3 factorial ways to pick all of the other digits. So that's a second possible solution. Any thoughts about this one? Okay. Any other problems that anyone would like to take a look at?
I was hoping
Question 9.
Number 9. Okay.
Yep.
I'll take that one. That was one of the ones I stuck on the test. By the way, Wendy, when you graded, what was the greatest number of problems anybody solved?
Let me pull that up while you do this, and then I will share that after you go through the solution.
Okay, so we have 2 restrictions for the numbers that we're trying to count. The 2 restrictions are that the number must have exactly 3 digits. Three restrictions. That these integers are divisible by 9, and then the digital sum is greater than 9. And I always like to list my restrictions and then take a look and say, hey, which one is going to kind of narrow the focus of what we're doing the most? Well, I looked at the last 2 and said, hey, there's kind of an interplay between these, because the divisibility rule for 9 says that the digital sum is a multiple of 9. But then the next condition says the digital sum is greater than 9. So now we know that the digital sum is, it's a multiple of 9 that is greater than 9. And there are only 3 possible digits. So the digital sum cannot be bigger than 9 plus 9 plus 9. So the digital sum has to be either 18 or 27. Now we've reduced the problem to a more standard counting problem. So for the digital sum that's 27, there is just one possibility. That's it, 999. So now we just need to count up the number of ways to make a digital sum of 18, and then we're just going to add 1 to that. So we might do casework. Maybe we say that, what if the first digit is a 1? Then the other 2 sum to 17. And that's either going to be 198 or 189. Or the first digit could be a 2, and the other 2 must sum to 16. And we have 297, 288, or 279. And what you can see is I'm kind of using something that we call the extreme principle to organize my casework. I'm going from the biggest possibility to the smallest within these cases. So I start out with the biggest possible tens digit, and then I just subtract 1 from it and add 1 to the units digit to go through these possibilities. And that helps me realize quickly that there are 2 here, 3 here. There's going to be 4 that begin with 3. They go 396, 387, 378, and 369. So 4 of them here. And we go all the way up to the case where the first digit is 9. And we can do 990, 981, all the way to 909. So we have 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 1. And that gives us 55 total. Any questions or thoughts about this one?
When you actually know how to solve the problem, it actually seems kind of simple. So we didn't have to solve for the others because it was showing a pattern that told us that it kept increasing in the number of cases. So we didn't have to solve for the other ways.
Yeah, so long as we understand why the pattern continues, then that's fine. The reason I went to the end and checked there is because at some point, if we had a digital sum of less than 9 for the last 2 digits, then we wouldn't have all the possibilities available to us. If the digital sum were 6 for the last 2 digits, we would go 960, 951, and we'd only get 7 possibilities in total. So it's good to you need to make sure that that a pattern continues. But once you're sure, you can skip the middle work.
Okay.
Okay, are there other problems anyone would like to take a look at, or would you like to learn about the divisibility rule for 11 and the divisibility rule?
We look at question 2.
Problem number 2.
So I'll just really quickly say the test statistics. So the one that Matthew just went over, I think was a tricky one for people because I don't think anyone got it right. Some people were close, potentially missing the case where it was like 999 or something like that. Some people were off by 1. And then the highest score on the test overall. So we graded 1 through 10, just 1 point if you got it right. And then 11 and 12 where you showed your work, I graded it on a 5-point scale, so depending on how close you were. On the first 10 questions, the highest score was 6, and then total, the highest score was 16.
So that's 16 out of 20 points?
Yeah, that's right.
Okay, any other problems anyone would like to take a look at, or should we talk about divisibility rules for 11 and weird ones like 999,999?
I actually thought we could look at question 2.
Okay, that's one of Wendy's.
Yeah, I can do that pretty quickly. Cool. So this is question 2. How many distinguishable towers consisting of 8 blocks can be built with 2 red blocks, 4 pink blocks, and 2 yellow blocks? And so if we build a tower, we're basically picking blocks to go, say like from the bottom up. And I can, in order to represent this easier, I'll just say red blocks, we'll represent them by a letter R. So there's 2 of those. There's 4 pink blocks. So I'll just use P. And there's 2 yellow blocks. And basically this is saying how many ways, I'm just going to change this to a different problem, but equivalent. How many ways can I create a sequence of these 8 letters where there's 2 R's, 4 P's, and 2 Y's? So for example, I could say R, R, P, P, Y, P, Y. And that might correspond to a tower where I
Yeah,
put a
there are
red
only,
block at the, sorry?
yeah, there are only 3 P's when there's supposed to be 4.
Good call. So maybe I'll put a P at the end. Let's say that corresponds to a tower where I do red, red, pink, pink, yellow, pink, yellow, pink, something like that. And so we can transform this question into the equivalent question of like how many sequences are there consisting of 2 R's, 4 P's, and 2 Y's. Any questions on why that is the case? Does everyone see why it's equivalent? All right, so if we think about that, we basically want to like order 8 different letters where we have multiples. So in our class this week, we learned about how to correct for overcounting when there's multiples. And so there are 8 factorial ways to order 8 distinct things. And so here we have 8 letters, but they're not all different. And so remember, to correct for overcounting, we want to then correct for the ones that are indistinguishable by dividing out how many ways there are to order those. So for example, we have 2 red blocks. And so there's 2 factorial ways to order red blocks. And since those red blocks are not distinguishable, we want to actually divide that from our total of 8 factorial. Similarly, we have 2 yellow blocks, so that's the same. And then finally, we have 4 pink blocks, and there's 4 factorial ways that those pink blocks could be sort of ordered around. And so this would actually give us 8 times 7 times 6 times 5 times 4 factorial, 2 times 2 times 4 factorial. And then I'll just kind of simplify this. And then this gives us 420. And then I did go into a little bit more depth in the lecture on Tuesday about how why it's how we motivate kind of dividing by these factorials. But if it's not fresh in your mind, I would recommend that you go and rewatch the video. But the part where we talked about it was when we tried finding out all the permutations of T, I, and T. And remember, we labeled the T's as like T1 and T2 and counted out how many there were. So take a look at that if this isn't jogging your memory. Any other questions on this problem?
No, please.
All right. Any other questions on the test people want to see?
I was
How about question 1?
3 and 4, but if Mr. Crawford said he wanted to show us something regarding divisibility rules, so maybe I can just ask on Piazza.
So somebody wanted to look at problem number 1. Why don't we do that real quick, and then we'll finish the lesson that we didn't have time for on divisibility rules. And Wendy, if you want, you could stick around or you could take off. Up to you.
All right. I think I'll drop off a bit early then. But if you all have any questions on any of the questions, definitely post on Piazza, or if you have any questions about any of the lecture material on counting, feel free to post and I'll get back to you on the forum. All right. I'll see you all next week.
Thanks, Wendy.
Thank you.
Okay, thanks. Bye.
Okay, let's take a look at problem number 1. We want to know, basically we want to know what are the remainders when we divide an odd perfect square by 16, and then sum up those possibilities to get our final answer. Mostly we just want to know what they are. Now, one thing I want to point out is the other day we found out that a perfect square could only be congruent to 0, 1, or 4 modulo 8. Right? What this means is that a perfect square could be 8 times an integer, or it could be 8 times an integer plus 1, or it could be 8 times an integer plus 4. Well, how many of these could be an odd number?
Only
Half of them.
Well, there's 3.
only 2 of them could be an odd integer. This last and the second to last.
Could the last one be an odd integer? What's an odd integer that we can write as 8k plus 4, where 8 is an integer?
No, it doesn't work. Right.
It doesn't work. We have only 8k plus 1 as a possibility. Every odd perfect square is 1 more than a multiple of 8. And there are other ways to see this too. If we take an odd number, like, write it in the form 2k plus 1 for some integer k, multiply it out, we get 8k squared, sorry, 4k squared plus 4k plus 1. And this is 4 times k plus 1 plus 1. And there's 2 ways we can think about this. This is 4 times the product of 2 consecutive integers. But if you multiply 2 consecutive integers, one of them is going to be even. So we have an extra multiple of 2 in there. So in total, we have at least 3 powers of 2 in that quantity right there. So we have 1 more than a multiple of 8. Or we could even say, hey, this is 8 times k plus 1 divided by 2. And that's 8 times k plus 1 choose 2, which is 8 times the number of ways to count something. And if you count something, you're always talking about an integer. So we have 8 times an integer plus 1. So, there's a lot of different ways to look at this, a lot of different ways to see this. Every odd perfect square is 1 more than a multiple of 8. So we're talking about, how these perfect squares relate to multiples of 16. What is the residue modulo 16? Well, if you write a perfect square, if you write any quantity, let's see, let me pick a color. Okay. If n squared is equal to 16 times an integer plus a remainder, well, then it's equal to 8 times an integer plus, I'm still going to call it a remainder, even though, our r here must be restricted from 0 to 15 inclusive, right? Okay. Well, having written this in terms of multiples of 8, I can now use what we learned before. We know that an odd perfect square is 1 more than a multiple of 8. And that means this r right here could only be 1 or 9, right? Because this part doesn't matter to us. It reduces to 0 modulo 8. So r must be 1 modulo 8. And just to be sure, if we say r could be 1 or 9, well, 1 squared is 1 and 3 squared is 9. we find the possibilities pretty quickly. So now what I've done is I've done, no simple arithmetic. We could just do this by casework. If this isn't good enough, we can do it by casework. We could say 0 squared is 0 mod 6. Oh, we only need to square the odd ones, don't we? 1 squared is 1 mod 16. 3 squared is 9 mod 16. 5 squared is 25, which reduces to 9 mod 16. 7 squared is 49, which reduces to 1 mod 16. But then all the rest are squares of the additive inverses of cases that we've already covered. So we're going to get nothing new from the remaining cases. So just 1 and 9, those are the only possibilities. This is the most straightforward way to do it, is just to go through the cases. But there are a whole lot of different ways we could see it, and what we know modulo 8 could inform us about how to get there in a more intuitive way. So the answer to this one is 10. 1 plus 9. Any questions about this one? It's kind of nice when you begin to build up your experience with modular arithmetic and you begin to build up your experience with the algebra to help with number theory. The two play very well together. And as you build that experience, you'll find more and more different ways to make them play well together. So now let's cover something that we didn't cover at the end of our last lesson. And there's kind of a nice leap from there that I want to talk about that it's kind of fun. So first we're going to talk about the divisibility rule for 11. And this is one, some school children get taught this at some point and some don't. There's not a huge need for it, but it can be nice and helpful. And the methodology is something worth learning, right? Who knows a divisibility rule for 11?
I found one for 4-digit numbers.
For just 4-digit numbers?
Yeah.
What's your divisibility rule for 4-digit numbers?
The first number minus the second number plus the third number minus the last number. When you add them up, they must give you a multiple of 11.
Right.
Else it's not.
And this works for any number of digits. We call this an alternating sum. We take the alternating sum, and if the alternating sum is a multiple of 11, then the original number is a multiple of 11. If it's not, it's not. I'm going to change this a little bit differently. I'm actually going to change the alternation of the signs. And here's the reason why I'm doing that. If we take the number 4, 5, 6, 7 and divide it by 11, we find that this is equal to 415 times 11 plus 2. And notice the way that I did it gives us the remainder. And I like my rules not just to be divisibility rules, but to be remainder rules. And if you perform your alternating sum such that it ends with a plus, right? Go from the right and work backward, plus, minus, then you wind up with the appropriate remainder. And let's see why. If we take this number 4, 5, 6, 7, we can rewrite it as 4 times 10 to the third plus 5 times 10 squared plus 6 times 10 to the first plus 7 times 10 to the 0. And now let's remember what we did when we were building up the divisibility rule for 9 or for 3, is we noticed that 9 is 1 less than 10. So we realized that powers of 10 reduce to 1 modulo 9, and 1 is so easy to compute with in multiplication, right? What's 27 times 1?
It's a
27. Okay. What is Archie Jane times 1?
Archie Jane.
Yeah, it's a multiplicative identity. We don't even have to do any work. So it was nice that we could reduce 10 to 1 modulo 9. Well, 10 and 11 are 1 apart. What can we do?
We could replace all
reduce-
tens by -1.
We can replace the 10s with -1. Very good. So modulo 11, this is equal to 4 times -1 cubed plus 5 times -1 squared plus 6 times -1 to the first power plus 7 times -1 to the 0 power. And this is not quite as easy as powers of 1, but it's certainly not hard. And there we have it. And, the alternating sum rule, it works, but I prefer the alternating sum where the units digit is necessarily a plus sign, and we go plus minus going from right to left, because it gives us a remainder, and sometimes that's useful. Any questions or thoughts about this one? Okay, so that's a divisibility rule for 11. Now, I told you that we were going to come up with a divisibility rule for 999,999. But I'm actually we're going to use a stepping stone. We're going to come up with a divisibility rule for 99. In fact, there's more than one way to do this. So if I asked you to come up with a divisibility rule for 99, what would you offer me? How could we do this?
Since 99 is a multiple of 11, so you can use 11.
Okay, so 99 is 3 squared times 11, or it's 9 times 11. And the GCD of 9 and 11 is 1, and the LCM of 9 and 11 is 99. We know that something is a multiple of 99 exactly when it is a multiple of both 9 and 11, right? So we could say a divisibility rule for 99 is that's divisible by 9, and we have a divisibility rule for that, and divisible by 11, we just developed a divisibility rule for that. And so that's fine if we want to work it this way. And even if we want to use these as remainder rules, we could, they're a little bit further on in lessons in number theory, you might find how to, in an organized way, find the numbers that have a remainder of 4 when divided by 9 and a remainder of 7 when divided by 11, or you could just hunt them down and know that their difference is going to be a multiple of 99. Putting that aside, that's not something that we've gotten to in class yet, and I think that that'll be held out for a higher level class. But there is an interesting way to do this without using the divisibility rules for 9 and 11. Now, 99, why is 99 interesting?
So palindrome.
It is a palindrome. Why were 9, what was interesting about the divisibility rules for 9 and 11?
For 9, you have
Addition
to
of the figures.
check the
For
sum.
9, the addition of the figures should be a multiple of 9, and for 11, we just learned it so.
Our divisibility rules for 9 and 11 revolved around the fact that they were very close to 10. In fact, they were 1 away from 10. So what's interesting about 99?
Is 1 away from 100.
It's 1 away from 10 squared. It's 1 away from 100. Good. How can we make use of that?
We could break it down into base form.
We can break it down into base form, but we can do something slightly clever. What might we do?
You can divide it by mod 100.
We could group the digits into pairs. And express those pairs times a power of 100, each one of those. What does that allow us to do?
Change them to 1. Sorry, -1. Mod 100.
Change them to 1 modulo 100. Sorry, modulo 99. Now we just take the sum of these 2-digit numbers. What is that sum?
A multiple of 9. Or 99.
In this case, it's 198, which is a multiple of 99. Therefore, the original number is a multiple of 99. So the methodology, group by 2 digits at a time, start at the right. If there's an extra digit out here, make it its own number, and then you would have like just that digit out front as its own 2-digit number. It would just be 4 times 10 squared to the 4th power. So when you group, make sure that you start at the right, grouping 2 digits at a time. That way, if you have an extra digit, you've organized it in the right place. So now, yeah.
Does that mean for the 999,999, we're going to do the same thing, but basically we are, instead of 10 squared, is going to be at 10 to the power 6.
Right. So Salorm, you're onto something. So describe the divisibility rule. Let's say that I presented you with a number that has like 24, or let's say 28 digits. How would you, make life a little bit easier instead of, doing long division with a 6-digit number and a 28-digit number? What would you do?
Well, because of what we just did, and we found out that 99, it's 1 less than 100. So I would say that 999,999 is 1 less than a million. So it's 1 more in mod 19, 9 mod whatever that long digit number. So then I would start pairing the digits like we did for 99 and start multiplying and start grouping the powers of 10s as 10 to the power 6.
Okay.
And then compare it to 1, and then add that number together and see whether it's 0 in mod 999.
Okay, I think you've got it right. I want you to change the wording just a little bit. You said start pairing the digits. What do you really mean?
Sorry, I meant find, as in like putting them together so that when you multiply them, they place exactly like they would in the actual number.
So let's be a little more explicit. How many are you putting together at a time?
It's a 28-digit number.
Mm-hmm.
So 6. it should be 4 at a time, but yeah, 4 at a time. You can put 6 numbers together at a time.
6 numbers together at a time, that's right. We would group it into 6-digit numbers, except at the very beginning, we would only have 4 in that first group. But otherwise, we would group numbers together 6 at a time to form 6-digit numbers, add those together. If that number is a multiple of 999,999, then so is the original 28-digit number. There we go.
Yeah.
So that one's probably not too practical. You're probably not going to find a whole lot of situations where you need to know whether or not something is a divisor, is a multiple of 999,999. But the methodology, the fact that we know that we can invent these rules by relating, relating different integers to things that are in the vicinity of powers of 10. And we can do that much more easily once we've learned our modular arithmetic. All right, let's call it a day. And I will see you all on Monday afternoon, Ghana time. I hope you all have a very good weekend.
Same to you, Mr.
Okay.
Crawford. Thank
Very
you.
much.
Bye.
Thank you. Bye.
Thank you. Bye.
Have a good weekend.
You
Thank
too.
you.